So this is another example which explores the differential relationship between current and charge as functions of time. Specifically, we're given a current defined as a piecewise function. Notice that over the first interval of its domain from 0 to 1, it takes on a constant value of 2 amps. And for all values of t greater than 1, it increases in a parabolic fashion as 2 times t squared amps. So even though the problem description doesn't provide a rule for assigning a value of the function at 1, we don't have to worry about it. If you do an evaluation, you'll find it's continuous at the point of discontinuity. So given the current, which of course is the time rate of change or instantaneous rate of change of the charge, we want to calculate the total charge entering the element from 0 to 2 seconds. So recall any time that we know the rate of change of something, we can calculate the total change in the quantity by simply integrating over the desired time period. So what I'll say is that the total charge entering the element over the period from 0 to 2 can be determined as the integral over the interval 0 to 2 of the current function. I'll use a dummy variable of integration tau, so that's I of tau d tau. Now recall that by the linearity of the integral operator, I can split this integral over the domain of integration. I can integrate from 0 to 1, and then add on to that the integral from 1 to 2. And the reason that I would want to make that decomposition is based upon the piecewise definition of the function. So here in the first interval, I simply am taking the interval of the constant function. That's going to be pretty trivial if you consider it as the area under the curve. It would be a rectangular area with a height of 2 and a width of 1, so that area would be 2 coulombs. The second is going to be a bit more complicated, only because I'm integrating under a parabolic area. Specifically, the function in that interval is represented by 2 tau squared d tau. So if I really want to show all of my work here, recall that in order to evaluate these integrals, I first need, by the fundamental theorem of calculus, to find the antiderivative of each integrand, and then evaluate it at the top and bottom of the interval and take the difference. The antiderivative of 2, right, the function whose derivative is 2, is simply 2 tau. We're simply using the inverse of the power rule there in order to calculate that antiderivative. I want to evaluate that at tau equals 1, evaluate it at tau equals 0, and take the difference. The antiderivative of 2 tau squared, or the function whose derivative would give you 2 tau squared, is simply going to be 2/3 tau cubed. And if you don't remember how to do that, increase the power by 1 and divide by it when taking the antiderivative of a polynomial type function. And in a similar fashion, we're going to evaluate that at tau 2, tau equals 1, and then take the difference. So in our first evaluation, when I evaluate 2 tau at 1, of course I get 2. When I evaluate it at 0, I get 0. Plus, when I evaluate tau cubed at 2, 2 cubed will be 8, right? And 8 times 2/3 would be 16/3. You can pull that constant out by the linearity of the integration operator if you wish. When I evaluate the cubic function tau cubed at 1, I simply get 1/3. So I'm going to be subtracting off this 2/3. So that's going to give me 2 plus, we have a common denominator for those fractions, we subtract directly and get 14/3. Getting a common denominator in order to add these would simply be 6/3 plus 14/3, which would give me 20/3, which would take on an exact value as a mixed number of 6 and 2/3. Now what would the units be? Well, clearly, just thinking about it from a physical perspective, we're taking the product of a function, which is in amperes, which has the equivalent units of coulombs per second, and we're multiplying by a time interval of seconds. So, of course, that would give us coulombs. If we wish to approximate that, that would simply be 6.7 coulombs. So let me rewrite that so that it's a little bit clearer. 6.67 coulombs approximately.